Okay, welcome back everyone. Today we are going to get into a new chapter, chapter 11 in BSL. We're going to start with, we're going to start with looking at the equation of changes for non-isothermal systems. So we have been dealing with using the combined energy flux vector, coupled that with the, shell balance technique to deal with a lot of examples, especially for laminar flows, or actually for also convective transport related problems. And in this chapter we are going to kind of extend that discussion a little bit further to a more generic form, and so that we are going to try to derive this equation of changes for non-isothermal systems that can be very generic and easily applicable to different scenarios. So let's think about, when we're looking at non-isothermal systems, what would be the most useful form of an energy equation? So that's the first question we want to think about, right? So what would be the most useful form of energy equation? So what do we care the most when we're dealing about non-isothermal systems? If you think about what we're doing in chapter 10, we're always trying to figure out the temperature profile of a system. And if we know the temperature profile, we know the gradient of the temperatures, then we can figure out the fluxes and the heat transport, right? So to answer this question, what would be the most useful form of energy equation, we can simply think of, we should try to get an equation that temperature appears. So the short answer for this is that we want an energy equation which temperature appears. So we'll say one of which temperature appears. So if you think about, if we come back and kind of revisit the energy flux vector, so if we come back to the energy flux, we use that to perform our energy balance, right? Okay, so if we kind of do a very rough equation on this, we know that the accumulation of the energy per volume would be the change in the energy and the change in the combined energy flux vector plus the work, right? So let's take a look what's going on here. So if we write that down, that's going to be partial T, that's the change with time, and this is going to be energy per volume. That would equal to the negative gradient of the combined energy flux vector, plus we have the mechanical energy here. Okay, and if you look at what is exactly the energy per volume, we have the kinetic term, the kinetic energy term, and the internal energy term, right? Okay, and if we look at the combined energy flux vector, we also have what? We also have the kinetic energy and internal energy transported by convection. It's kind of like a review at the moment, times its velocity, plus the heat carried with it plus the work associated. So this is the PV work, and also we have the work coming from the shear stress. So plus the shear stress term. So if we kind of expand the equation to its full form, we now have the following. We have on the left hand side the change of the kinetic and internal energy per volume of the fluid. So the kinetic and the internal energy per volume of the fluid equals to the gradient of the combined energy flux vector, which we have a lot of terms, right? So we have the convective term, heat transfer, and the work associated. Okay, so let's write that down. So we have 1/2 rho v squared plus rho u times velocity minus the gradient of heat minus gradient of PV work minus work by viscous force and also we have the last term here, which is other external forces like gravity. Well, let's kind of pinpoint it down. So we have a convective term here, just to make it easier to understand. We have the convective term, we have heat conduction, we have work by pressure forces, we have work by viscous forces. Pen is not working really nicely today. Work by viscous forces. And we also have external forces that's going to exert or going to, give work to the system. External force like gravity. So, we have, this is like a very, very generic form. We are kind of by using the sorry, I don't know if this is working. Let's give it a quick shot.